Welcome everybody to DevOps and to our Reactive Transactions Masterclass. So this talk will be split in 3 parts. We will go over how imperative, how reactive transactions work, and then dive into R2DBC and Neo4j. And with me is my friend Michael. So who am I? My name is Mark Paluch. I'm Spring Data project lead. I'm maintainer of the Lattice Redis driver. I'm also a contributor to the R2DBC project, which stands for Reactive Relational Database Connectivity. And as you might already see from that, so all things open source, all things reactive for me. And you can find me on GitHub, on Twitter, on my website, Paluch.biz. And this is Michael.
Yes. Hello everybody, welcome from my side as well. I work for Neo4j. In contrast to other thing you heard, I'm not in developer relationships. I'm an engineer at the Spring Data and drivers team at our company. I happen to also have written a couple of books, one book about Spring Boot 2 and one about the Arc42 template. That's something you can document software architecture with. Apart from that, I'm contributor to a bunch of open source projects as well, and I really like that work. But I also run, I bike, and I take pictures, and that's a book I'm working on at the moment. Personal thing of mine, but if you want to have a look at it, you can go there. This year again, I will spend all the revenue from that book and the Arc42 book on LeanPub again on Medicines Sans Frontiers. I think that's something important to do once in a while. We have all the code of our demo on GitHub. There's a short link to that, RxTX on Bitly. All of the demos we have and all of the exercises we have work with embedded databases. That is true for the H2 database, which we use for R2DBC, for Mongo, and of course for Neo4j. So, speaking of money passing around is something you would have transactions for. And with that, we start with the way imperative transaction works. First, of course, a regular transaction. Someone with money in a bank wants to give money away.
Oh, thank you, Michael. So this means that you are spending the money to Medicines Sans Frontiers?
Of course, yes.
Cool. So let's initiate that bank transaction from the person who has money to the person who will receive the money. So as a prerequisite, we have a couple of actors here, and we have a subject that this transaction is all about. And the subject is basically wiring funds from one bank account to another. How do we do that? Well, we set up a transaction, and this transaction basically means send a fixed amount of money from one account to another. Do not split that amount during that transaction, but keep it as an atomic unit. And everything happens either or it doesn't happen at all. And this is one of the keys. So we are wiring these funds over to the other bank account. It's gone from the source account and it has arrived at the target account, as it should be. Now, transaction is done, transaction is committed, and we are grateful as receiving the money from you. So everybody is happy right now, right? So that's a happy case. But you aren't here today to just hear about the fancy and shiny happy cases, right? We are basically here to learn what can go wrong and to learn what we have to watch out for. And let's directly dive into that. Now, there are things like phantom reads that you might have heard about. And let's see how this actually works in the scope of a transaction. Again, we have this example of these 2 folks, 2 bank accounts. We are wiring money from one bank account to another one. And let's initiate the transaction. The money is flying over from one account to another. But it didn't quite arrive there yet. However, we see that the money is gone from one bank account. And we see it already on the target account, which is sort of strange. And the receiver probably does not know that the transaction is still in progress. Only the sender might know about that. So what can happen is that the receiver sees the money. Yeah, it's there. And starts buying because, hey, we have lots of money.
Go to Amazon shopping.
Exactly. Let's buy the newest iPhone, Android phone, whatever. Car, presents, right?
Bike.
Exactly. You're a biker. But now what happens is there is somebody with a proper transaction management implemented. And this transaction management sees a timeout or some other condition to roll back that transaction, which basically takes the money away from that account, performs a rollback, and this guy is like, whoa, what's happening here? I bought all that stuff. What about now? Do I have to return all the presents? What will my family say that I can't buy my 2-year-old the newest iPhone, right? Now, the money goes back, and in this case, luckily, something strange happened because the other party can keep basically the presents. Now, this is sort of like a phantom read looks like. We see already the terminal state of the transaction, the outcome, but the transaction wasn't quite done yet. Now, the other guy wants as well having phantom reads, because that's only fair, but this is an entirely different story. Now, what if you start implementing your own transaction manager? Because we are developers, we think that we can do it. So what does it really take to build a transaction management? Let's try that. Now we are again back in our scenario with the banks, with money. We are wiring funds to another account. But what this time happens is that we probably made a mistake. Typically software is bug-free, unless we get the bug report, right? And in this case, we didn't take the money away from the source account and wired it directly to the recipient. So we have two happy parties, and the only one who fails right now is the banks because they go bankrupt. So probably not the best approach here, right? There are also other kinds of things that may happen when a transaction breaks. So in reality, if you are a bit into banking, then you know that banks do not do these atomic kind of transactions that we know from our SQL database or any other ACID-compliant database, but rather what they do is they initiate something which is distributed, and at the time you start wiring money out of your bank account, it's gone, but it's not there at the target account, it's somewhere in flux. And what could happen in such a scenario is that this transaction gets stuck. And probably this is not good because it's gone from a first account. It never arrives on the second account because some transactional zombie kicks in and then takes away all that money. It's gone and basically nobody has anything from that. So we are left with two push marks.
I see what you did there with saying by transaction is in flux, right? This must not always be a transaction zombie or something evil. It can happen in scenarios where we don't expect it. And
exactly.
Connection goes away when browser goes away, and I think we will speak about it in detail.
Exactly.
So that is a quite common scenario here.
Now, transactions are all about a couple of things. So we want to ensure atomicity. So either everything gets applied or nothing gets applied. We do not want to have a state which is inconsistent because we did only apply half of the work. This is the state that we want to avoid. What we also want to achieve is that we isolate all the remaining participants in a transactional world from each other. So when I'm wiring funds from my account to Michael, then nobody else should be really affected by that. So if Michael gets money from any other place, this should be independent from that, and nobody should see that there are transactions going on while they are still active. So this is the thing that we mean by isolation. We want to end up within a consistent state. And no matter whether this is due to changing things or due to reading things. So every time we read a particular record, a particular row, we want to receive and see the very same state and not something that changes over time when our transaction is active and when it is running. And clearly, to achieve that, we need something like a transactional resource.
Fun fact at this slide, we managed to create a transactional bug. We fixed the slides beforehand and mentioned that the transaction needs to be durable as well, so that the money doesn't go away.
Exactly.
And somehow that transaction of our slides is still in flux. It's really easy to get
right. Exactly.
Wrong, I'd say
it should be durable, and yeah, we didn't make it durable. So what do we need in order to make a transaction run? Well, we need a transactional resource. And a transactional resource can be something like a database connection. And when we are dealing with resources and transactions, we call them resource local transactions. There's an entire different flavor also of these transactions, but for the moment, let's stick with resource local transactions. So this means that we need to get hold of that transactional resource from somewhere. We then apply our work, and afterwards, we clean up the transaction. And this can be either rolling back the transaction because we encountered a condition that needs a rollback, or we perform a commit. So we must not keep that transaction in some limbo state. Otherwise, unexpected things might happen. And for a database, this is pretty straightforward. What we do there is opening a connection. When we're using Java, then we probably use also JDBC. We get a connection. We disable auto-commit mode, which translates sort of to beginning a transaction. Then we apply our work in the form of running SQL queries. Important bit here is if we run multiple of these queries, we have to reuse the very same connection, because the transactional state is bound to that connection. If we would use a different connection, then we would run into the state of isolation, because another connection cannot participate in the very same transaction, right? And afterwards, we call either commit or rollback. And to give you a short impression of what this really takes is, therefore, we will switch to our demo. Now, here we go. So I have this JDBC JUnit test here, and when I work with JDBC and directly, let's go into presentation mode. Then I deal with the connection. Afterwards, I have to create a statement. You know, JDBC is really fun to use, and what we do there is we run an execute update and insert some data. And you know, transactions are all about consistency, so you have to cater for your t-shirt that it matches basically the test data. So we are Breaking Bad themed right now. Now, what happens here is I'm executing an insert statement. And to demonstrate properly transactions, let's have something second to do. Because in auto-commit mode, typically you are at a granularity of a single statement, and it starts getting interesting if you deal basically with multiple statements. Now, let's run that. We are inserting rows into two tables. One is a person table, the second one is a person event table. And since this is a happy case, everything was running basically smoothly. It starts, however, getting interesting if we encounter some failures. Let's repeat that, what we basically start with. We are inserting two records. And let's enforce some use case that would basically create some sort of race condition. And to do so, I'm deciding to remove that row from my person table. Delete, Jesse. And since I'm also having an audit log with this person event table, I want to insert another audit event that I have removed that record, basically. Now, let's run this. And what we will see is that we run into a failure. So the primary key that I use here is a duplicate. And you can heal code by just putting a try-catch around that and basically, go with that. And this makes all the code work, except that if we take a look what the current state in the database is that we have deleted a row from the person table, But in the percent event table, we have only this created action. We basically miss another one. So let me fix that statement to show you how it basically should look like. The person table should be empty, and we should have basically 2 rows in there, which says one is created, second one is deleted. And this is one of these effects that you encounter if you work with things that should be atomic, but they aren't. And the proper way how to deal with that is basically use transactions, right? So let's repeat that and deal with transactions. To do so in JDBC, I'm disabling autocommit. There is no begin method in JDBC because every driver itself has to determine when to basically start with a transaction. Then we commit and run the next batch of work. And in this case, we are recovering in the sense that after the exception, we are rolling back. Roll back, here we go. Now let's run this. And then the exception, which happens, no exception happens because I copied the wrong thing. Now, and then the thing that happens is we run the code above, so inserting 2 rows, commit it, and then we run the next block that is basically applying another set of changes, so deleting a row from person and inserting into person event. And when we look at the result now, then we see that we basically didn't apply that transaction. So due to the rollback, the Jesse is still in the person table, and we see only this created event in the event log. And this is actually how it should be and how it should work in a correct transactional way. Now, there are a couple of more items to transactions themselves. So we are able to control a few properties of a transaction, like an isolation level, which allows us to tune performance versus the properties that we can encounter during a transaction. So we basically can say, okay, we want to serialize everything, which is the highest level of transaction isolation. But therefore, we have to pay with resources on the server side because the server has to maintain that state and that visibility of actions. Or we can take a lower isolation level and say basically, okay, I want to read uncommitted, which basically is no isolation at all. So I'm able to look into a state of an ongoing transaction without really that transaction having to be committed. We have this explicit versus auto-commit mode. So auto-commit mode is as well a transaction, but this applies only to a single action. So I can insert something or update or delete something, and even a select opens a sort of a transaction. But as soon as I want to apply multiple of these statements, I'm no longer able to use auto-commit mode, otherwise I can end up with an inconsistent state. And there are things like read-only optimizations that help us to use cluster setups that have things like read-only nodes and these kind of things. And these are probably things that we want to incorporate into our flow, into our requirements themselves.
And regarding especially the read-only modes, and they are often just implemented as hints to the specific JDBC driver, or in our case, in my case, the Neo4j driver, it does exactly this, what Mark just mentioned. If you set up the Neo4j database in a clustering environment, then there will be leaders who accept writes and reads, and there will be followers who only accept reads. So, and with a transactional marked as read-only, we can decide whether we can use a follower or we must use a leader to distribute that query. So it depends on the database you're using whether those hints are actually taken into consideration or not, in contrast to the isolation level and the explicit commit mode, of course, which are hard requirements.
Okay. But Michael, would you really love to write all this transactional code using JDBC?
Of course not.
Probably not, right. That's what I assumed, and I assume the same is true for the majority of you as well.
But having said that, it's getting inspiring from an API like JDBC is quite helpful. So in our demo code, we have also demonstrations for the Neo4j Java driver. We are trying to be pretty clear of what is an implicit transaction, like running JDBC in auto-commit mode, or whether we want to have an block of statements we want to execute an explicit transaction. But I'm going to show you later how that works in our specific implementation.
So instead of doing all this manually yourself, what we actually want to do is explain to some component how the properties of your transaction should be, what the transactional behavior should be, how we want probably propagate the transaction if you deal with multiple resources. And all this is called transaction management. And a transaction manager applies basically the transaction definition to your resource, to your unit of work that you are starting. And it also allows you to use multiple units of work and express whether you want to combine these units of work into a single transaction or whether you want to start other transactions that should apply this work outside of the first transaction to basically isolate that work. If something happens in the nested transaction, then the first transaction is probably not affected by that. There are various implementations for transaction managers. Most known are for JTA, which is the Java Transaction API. And the second one that is quite popular is Spring's transaction management. There are also, like Michael already mentioned, driver-specific variants of transaction management, but these are really intended for niche use cases where you don't use either JTA or Spring itself. When living in the Spring realm, there are these so-called transaction manager implementations, and we have quite a few of them. If you want to use JDBC transactions, then you take a data source transaction manager. There's one specific for JPA, there's one specific for JMS. If you want to use MongoDB transactions, sorry, then you take the MongoDB transaction manager, and if you want to use Neo4j transactions, you use then the Neo4j transaction manager. What all they do is actually a bunch of things. So the way it basically goes is that you enter some scope of a transactional unit of work. You enter that by either saying programmatically, okay, I want to begin a transactional scope from here, using some utility, some API, or you enter a transactional method which is typically annotated with transactional annotations or similar. And what then happens is that the transaction manager allocates a transaction, and basically it actually checks whether there is an ongoing transaction and whether we should join that transaction or whether we should create a new transaction. Once this is done, we allocate a transactional resource, so a connection, and bind it to that transaction. And in the imperative world, this is binding a connection to a thread local. Because in the traditional programming model, the imperative programming model, we assume that all activity happens and stays on a single thread. We typically do things like preparing the connection for the transaction itself by applying the transaction attributes, saying whether this is a rollback only transaction, whether it's a read-only transaction, what the transaction attributes regarding isolation level are, so all these kind of things. And then the actual unit of work gets applied on this connection. And every time we interact with our data access API, the data access API makes sure to look up whether there is a bound connection to that transaction, and then reuse as well that connection. So we must not use any new connection because this would basically break how transactions work. Once we are done with our work, either successfully or completed with an exception, then we exit that transactional scope. And again, then the transaction manager checks whether we are in the scope of an already ongoing and nested transaction, or whether this is the highest entry point and we are eligible to clean up that transaction. And depending on what happened in that unit of work, whether an exception happened or whether we finished everything successfully, we either commit that transaction or roll back. So a cleanup happens. And what also typically happens is we run these so-called synchronizations, which allow us to apply after a transaction some bit of work, probably for restoring auto-commit state, for restoring the isolation level, so all these kind of things. And once this is done, we can then unbind the connection and release it back to the connection pool. So there's quite a bit involved into transaction management, and that's probably why we might encounter a bit of stack trace depth there, right? But from the user side, it's very convenient. So let's take a look what it takes to have this as transactional method, and again with our JDBC test case, right? So we have basically the same setup here. And if we want to apply a bit of work, well, we are now here in the Spring realm, that we don't deal with a statement and connection directly, but rather with JDBC operations. Let's execute the insert Jesse statement. So insert Jesse into person. Let's insert the event. Here we go. And also recreate that error scenario right now. And then delete Jesse from person and add that malicious person event that basically causes our transaction rollback. Here we go. Perfect. So let's run it to see that it fails. Yeah, that's actually the fun case to see demos fail. But this is by intent. Now, let's put all that into a try-catch again, because try-catch makes everything better, as you know. And we will end up with the same sort of race condition that we have deleted the person, but the delete event is, we have a single event in there. The delete event didn't make it. Now, to guard all that, we have two ways. The first way is the programmatic way, using transaction template or transaction operations. That we can call this either execute method if we want to return a result, or execute without result, and run all these statements within a transactional scope. We do the same for this failing sequence here. And what we will see is that we will be able to roll back that malicious transaction. So we see that this delete wasn't applied, and also this insert event wasn't applied. So we are back to a consistent state. So this is an example of, for programmatic control of transactions that we use this transaction operations. It has a couple of methods that we can use to control that transaction for whatever reason, right? Now, if we want a bit more convenience, then we probably want to watch out for methods that are transactional. So I have prepared this transactional service here. It is annotated with @transactional. Important bit, make this all public if you don't use interfaces. Otherwise, you might run into surprises, because in this mode where I don't use interfaces, Spring basically creates a runtime proxy using cglib, and if that class is packaged private due to restrictions on the class path and the class loader, we aren't able to basically subclass it. So make sure to have everything public or use interfaces.
As a nice sort of error is making the class public and the method package protected, because we don't fail at that time. We just don't happen to run in a transaction. So if you see transactional methods which aren't public and you don't use interfaces for your services, you don't run stuff into transactions.
Good hit. Cool. So let's use that transactional service, which basically does all the demo code that we've seen earlier. And what we do here is we get that transactional service injected. Let's call the insert method. Let's call the delete method. Let's see that test fail. And by the way, never trust a test that you haven't seen fail. So this is failing properly. Let's add my happy path try catch to that. Make the test pass. And we see, again, the same result, that we have one row in the person table, one row in the person event table, and we have a consistent state. So everybody is happy right now. So what about this bound connection idea? See, transactions were invented probably back then where at least I was born. So I was born in the 80s. And transactions are in place since at least the 70s.
I was born.
Probably the 60s. And the way it worked back then is you have one of these connection objects. You talk with your host. And this is probably it. You don't even think about a second connection, right? And if you think, then you're probably doing it wrong. So from there on, this convention evolved that we have one connection, which has one transactional state associated with it. As soon as we open another connection, we get a new transactional scope. So we cannot really merge these two connections to a single transactional scope. A lot of bad things might happen there if I run commit on one connection, but I'm still active in another statement on the other connection. So all sorts of problems can arise from that. And that concept has been propagated also to the newer world, where we have things like multiplexed connections for like Oracle or MongoDB or Neo4j, where we have perhaps no longer have this connection-bound transaction, but a session-bound transaction. And this transaction is really tied to that session, and still it isn't really portable. So therefore, we have to bind a transactional resource to whatever transactional scope is going on.
So that bound connection will be, I think, very important for some edge cases we will see later on.
Exactly.
Especially in the reactive world, you have to be really careful about using the bound connection.
And this binding the transactional state to my unit of work and all the associated resources is kind of important, because without this building block, transaction management, as we have seen it with Spring right now, wouldn't work. We don't pass a connection anywhere, but rather it is bound to a thread local, but that's really invisible to us. Now, with imperative transactions, there are certain limitations imposed on our code. We assume that in an imperative world, we don't deal with threads, or at least somebody else is dealing with threads. So the gist of this is our code, our processing resides and stays on the very same thread. Therefore, we are able to leverage thread local storage for all this transactional metadata, all synchronizations, all resources. And as soon as we spin up another thread or give that transactional piece of work to another thread, basically everything breaks. So don't do that. There are, however, approaches to offload work onto another thread, either using that async annotation in Spring, or if you live in a Java Enterprise world, then you have this managed executor service. However, if you start that transaction on one thread, you cannot continue that transaction in the next unit of work, but rather what happens is that you get a new transactional scope in there, because you could do all sorts of nasty things, so operate on the same connection in the two threads, and this really asks for trouble. So what there really happens is you start a new transaction, and then you spin off your work on that thread. Now, this brings us to a key insight, which is imperative transactions are fully synchronous. So this means that we have a time dependency across these steps, and we must honor as well this dependency. We cannot start introducing concurrency into that flow, because this would basically break everything that really runs here. Now, how does this time dependency look like? Well, it is the fact that we have to have a resource before we can begin a transaction. We have to begin a transaction before we start the work. So we have to wait until the transaction is started. we can only work after the begin, right? We have to apply our work before the transaction is getting cleaned up. So we must not basically drag our work outside of the transaction scope and clean up the transaction while some activity is going on. And finally, the transaction cleanup can only happen after our unit of work is finished. So that's basically the anatomy of such a transaction. There's one other kind of transactions. We have learned so far about resource local transactions, but there is this flavor of distributed transactions. Now, how many of you have worked with XA? Okay, and who enjoyed it? Yeah, exactly. So this is actually the issue with distributed transaction. It kind of works. There is a specification which tells you how it should work, but in most cases, it turns out that distributed transactions are not the most fun, although you can really distribute your work across multiple transactional resources. That's what it's all about. And to make these things work, you don't work in auto-commit mode or something like that, but rather you have this two-phase commit protocol, which goes basically to each involved and participating resource that asks, are you ready to commit? Yes. The next one, are you ready to commit? Yes. Okay, then commit both. And how it typically goes is that you don't commit both resources at the exact same time, but rather these things go sequentially. So if you lose a connection there, then basically good luck with that. Now, you can still do things like distributed transactions, kind of, in things like in an arrangement like in Spring Framework, where you use like Redis and JDBC together. Redis, well, it can do transactions. It's not the most fun thing to do, but still, you can. And if you do so, then what happens is you have one leading transaction manager. That would be probably the JDBC transaction manager that starts the transaction on the JDBC side. As soon as you use Redis in your transaction, the Redis resource just joins the transaction and registers a synchronization. And other resources may as well join. But this is not a transaction in the XA sense.
That's at least how we at Neo4j got to work with R2DBC as well, because we wanted to write tests for our reactive transaction manager that is able to join the leading transaction manager or provides join points for a transaction manager. So I think it was a great work together on open source, right?
It was, but still... commit and rollback is independent from each other. Yeah. So what happens in that case is that the synchronizations get invoked after cleanup, which means either rollback or commit. So both resources would be committed or rolled back independently from each other. But really, what happens if you commit the first one and then on rollback on commit on the second one you encounter some error? So don't do it. Well, at least not in that way. And this brings us already to reactive transactions. Now, we've seen how imperative transactions are supposed to work. Let's talk now how reactive transactions are supposed to work. And guess what? With the example of the database, you go to your database, open a connection, begin a transaction, apply work, and then you clean up. And this isn't kind of different from imperative transactions. Actually, that's exactly the same way how imperative transactions work. Because transactions are not about code, about flow, about synchronization, about futures. Transactions are a protocol which is to be implemented by somebody that wants to work with transactions. So we are talking here about a pattern, and we have the very same pattern here. We have to get a connection, begin the transaction, do our work, and then perform a cleanup. So it's that easy as it is. Okay, now go home, and we're done, right?
Wait.
No, we aren't. So when we are talking about reactive transactions in that scope, then we probably do not want to work with SPIs themselves, although we could, but rather we love convenience and we enjoy working managed transactions. So let's discuss which transactions managers we see in a reactive Spring environment. We have a couple of them. There is a R2DBC transaction manager, which is for SQL databases. So in the imperative part, we have that data source transaction manager. In the reactive part, we have the R2DBC transaction manager. There is a Neo4j transaction manager that takes care of Neo4j transactions using reactive APIs. And there is a MongoDB transaction manager for the reactive MongoDB driver that are already available with Spring data implementations. They all basically do and look the same in the sense that they are allocating resources for the actual transaction. They also check whether there is already a transaction going on and whether they should participate on that transaction or whether they should create a new transaction. The key difference, however, is in the technology, how we are binding the state and the resources to that transactional flow. If you remember, in imperative, we stay on a single thread. In reactive, we basically do not care about threads, but for a different reason. Because in a reactive programming scenario, thread switches can happen at any arbitrary time, because our code that is written in a reactive manner reacts to the availability and processability of resources. Not the way that we get a thread assigned, but rather that our code is called on some available thread. And we have no control over the time where thread switching really happens. So based on this knowledge, we cannot no longer use thread locals, right? Because that would basically break everything. Therefore, we have to find a different way how to bind our transactional state, transactional context to what we are doing. And in a reactive world, everything that we do is represented as a subscription. We have that kind of publisher that says what to do and how to do it, but to materialize that flow, we need to subscribe to a publisher, and we get back in return a subscription. And this is the point where the transactional resources for reactive transaction management are bound to. So they are tied to that particular subscription. And if I try to execute a particular transaction multiple times, then for every execution, I get a new subscription, and this gives me isolation across multiple invocations. And the rest basically goes the same. Once we have bound the connection to our execution, we have to prepare it to disable auto-commit mode, yada, 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 all the fun things. We issue our queries, apply our work. And in that space, the thing that we are using to do our work also has to look into the bound bound resources. So it has to look up the bound connection from somewhere, and this is again this subscription object. Once we are done with our work, we exit the transactional scope and we clean up that transaction. So pretty much exactly the same how imperative transactions work, with a slight difference regarding the opinion of threading and how APIs basically look like. Now, guess what? Reactive transactions are fully synchronous. Even if we are talking about being non-blocking in that space, we still have that time dependency, although everything is non-blocking. This is true for all the threads, and this is true for the time where we are waiting that some I/O operations are going to happen. For instance, the begin call. It takes a while to send it out to the server and to have the server to reply us. And at that time, our worker thread is idle, but still we have this synchronization in place that needs to await that the begin has happened, and only then we are able to progress with the next bit of work. So it's when you watch that conversation, it's always a little bit of back and forth and a dance between the components that are running. So we must not just start every single thing, begin our work and issue a commit directly without further synchronization, but we really need to await that the previous step has finished, which is the time dependency in transactions. So We have to issue a begin before we start with our work. We only can start work after the begin has finished. We need to complete our work before we can clean up that transaction, and the cleanup logically has to happen after the work has been completed. And these are synchronization points that are enforced by the reactive transaction management itself. So you don't need to really worry about these kind of things within your own application. You just write that code as if it would be any other regular piece of reactive code. Now, to compare both imperative and reactive, we have these various aspects that play into that. While imperative transactions are fully staying on a single thread, in a reactive transactional world, threads may change. And this is something that you do not have really control over because there are certain optimizations in reactive frameworks. There are I/O threads that you do not really control from your side. And so expect that threads may change. While we have in imperative transactions this thread local binding, we have in reactive transactions this subscription bound transaction status binding. And the next one is actually a fun thing. So in imperative transactions, we deal with imperative data structures, lists, iterators, iterables, these kind of things. In reactive transactions, we deal with streams. And one key aspect of a stream is that you hand out that publisher or flux or mono or whatever you use out of your method. So the data that is supposed to be processed within a transaction can escape actually the method. And this is a fun thing to think about, that you already emit data to some consumer while the transaction is ongoing, and at some point you either commit or roll back the transaction, and you have to expect that aspect of processing in your downstream code. So probably it's a bad idea to stream out changes to some other transactional system while your actual transaction is ongoing, because you have put the data already in some place while the original transaction might be rolled back. We will take a look on that, how it looks like in a couple of minutes, and what you can do about that. And the last point here is the synchronization. So both imperative and reactive transactions have that synchronization because of their time dependency, because that's what the transactional protocol basically enforces. Let's talk about cancellation.
Great fun for everyone, and took us a while, at least me, to get right.
Sure.
So, wait. That part I would rather help you do.
Sure, but I think before we get into that, let's set a little bit of the context, right? So this example here uses the idea of HTTP client and server. We have on the one hand a client, on the other side a server, which communicate over HTTP. And fun question for the audience: if the client gets disconnected, what do you think will happen? Will the processing on the server be cancelled? Hands up. Will it go on? Yeah, that's the right answer.
Oh, does it depend? In which case, what is on the server on the other hand, right?
Probably, yeah. It was probably a tricky question to say just yes or no without having further context. But really, let's walk through that. So we have that client, we have the server. We are posting some data from the client to the server to process a fair amount of data on the server side. Now, processing starts. It works first on the server side, then it stores the data on the database, and everything's good. Now, for whatever reason, we have this evil devil, this evil network devil with his magic network scissors that comes up while the processing is still ongoing. It makes snip, and the connection is gone, right? So, and as we would expect, the client is like, whoa, what's going on? But the server doesn't know about that, at least when we are talking about servlets, because there's no way how to know about that if you don't interact with I/O on the server side.
And saying that again, it does not need to be the evil network devil, especially not in the post scenario here. It could be the user who doesn't wait for a form to be processed and who closes the browser, or worse, just hits refresh a couple of times.
Exactly. So let's send the devil to another server and leave us alone. So in a reactive world, it could be different. So while in an imperative world, we have to stick to that servlet protocol, let's take a closer look at what reactive streams, which is the underlying specification of all our reactive effort, gives us. Well, we have this publisher and subscriber, which have a relationship. So the publisher emits data, emits completion signals and error signals from his point to the subscriber. And the subscriber has a channel back to basically request data. And now we have also another channel, which is the cancellation channel. So a subscriber can basically tell to his publisher, I'm done. Please do not send me any more data. And then if we translate that to a web scenario, the publisher is basically our data source, and the subscriber is that I/O channel that sends the data to our client back. And to illustrate that a little bit more, let's go into yet another demo. So we have that a case with servlets. Let's go through this first, which basically does the following. We have an endpoint that accepts a post. It is doing some heavyweight work for waiting for 60 seconds to process, so that we have sufficient time to cancel that process. Let's run that. Here we go. No, we have something else running on port 8080, which is probably... Is this one?
No.
And no, it's something different. Then, you know what? Then let's change that port. So port, and go to just a different port to fix it for now. Cool. So again, let's start our server. Our server is running. Let's get here some console and issue a post to our service. And we see run 0 from 0 to 10. Then we are processing. Then in a couple of seconds we will see the next round. And everything is going on. I'm canceling my process, but still the processing is going on, so the server does not know about the broken connection, that my connection is basically gone. So it's still processing, and depending on how the server is actually implemented, whether it is reading still data from the input stream or writing to the output stream, it may be that the server will encounter an error, but that's not really guaranteed. It depends pretty much on the implementation of that server. Let's kill that one and go over to a WebFlux application and start that one. I assume that I won't have to need. Yeah, I have to change that port here as well. So port, go to 1990 for whatever reason. Now we have basically here the same arrangement. We have a flux that emits every 10 seconds a value, so that we end up with something that runs roughly 60 seconds. And this stream is then given to a repository which saves things within a transaction. Now let's have that same fun here. We are starting something, and it is going on and on and on. We are canceling that process. But our server side does not know about that, because, again, it's also not interacting with the I/O channel. But I think we can do something about that. So there are customizations that we can apply to listen for things that happen on the I/O channel, because in the end, we're using Netty under the hood, and we can benefit from that. So let's do this one more time, and now pay attention. Hey, we have this cancelled here. So this is neat. So
That's
now
great.
our processing has stopped. But there's another side of that. So probably you have noticed that there is this at transactional over here, and this has some implications. So Michael, would you like to explain us these implications?
Yes. So what we see now is that the cancellation happens when there are network issues, when the browser goes away or the query request goes away. Cancellation happens also if I take only first elements of a flux or mono, or take n, or use the limit request. So the cancellation signal is sent upstream, like in thank you, I don't need additional data. But what happens with the transaction running upstream? In the case of Neo4j, I can easily write a query that generates a bunch of nodes from a list that I can unwind, or I use some kind of pattern comprehension to generate data. What about that transaction? Is it supposed to die with the request that goes away, or should it actually complete, commit, and be stored? So the connection is dead, it's cancelled. We decided that on a take n and on the cancellation, that we treat it actually as a commit, as a success. So transactions will be committed on a cancel. So it is not seen as a failure. Cancellation is considered as a success, but a cancel subscription does not await completion. And that's a sentence, I tweeted it some days ago, 6 words full of pain. At least took me more than a day to really grok this and to really get this with our driver team correctly. So basically, in short words, it means that a commit on a cancelled transaction may not be yet visible to following steps, to subsequent operations. And I'm going to show you this in some kind of Neo4j code. We go into the details of the code a bit later after our break, but it's nice to illustrate stuff. So what we have here is an instance of our Neo4j driver on the same level, I'd say, as the R2DBC driver. It offers a publisher of an RX session, which is a reactive session. We use that pattern of a transaction that is bound to a session. The session borrows a connection from a pool. And on that session, I run a Cypher query. Cypher is our query language for the database. And that query there creates a range of 1,000 elements and uses that index to create nodes. And then map that result into an integer so I can deal with it. And when that thing is done, the session is closed, and with it, the transaction. That's our take on auto-commit mode, by the way. So I just take 5 nodes of it. Or be even more explicit, in this case, using a step verifier from Project Reactor to express some expectations on the first 5 elements and do an explicit cancel. And then I verify that this stuff actually has been completed, or in this case, cancelled. So that works. Our transaction will be written to the database, even in a cancellation scenario. But can I verify it, whether it has been written to the database or not? So in this other query, which I will issue after the previous one, I count the number of nodes in the database that have been stored, get the result from it, map it to a long, and express an expectation on it. It should be 1,000 nodes. The answer to that question, can be verified, depends a lot. In my test, doing nothing between the cancellation and the verification yielded that I cannot verify the written data, but in the end the data has been written. We can see it in the database that it works as intended. But on the client side, you have basically no safe means of verifying that the transaction has been written in that case. Having said that, these cancellation scenarios are quite hard to deal with. In the customization that Mark showed us previously, on the netty by disabling the auto-read mode or enabling the auto-read mode. It kind of changes the whole behavior when netty should actually wait for incoming input from the thread it reads on, from the I/O it reads on, but it changes the whole behavior of stuff. So again, cancellation happens when the browser goes away, and the reason why I'm mentioning it very often is that we see a lot of demos also at conferences like DevOps, where it's very easy to just return a web flux from a Spring Reactive endpoint and just deal with it, probably in conjunction with server-side events, which takes another whole turn on transactions. And doing that with transactional flows will be error-prone. It will lead to all kinds of suffering, pretty much like the same way add transactional on a web endpoint in a plain way without an intermediate service will probably do. So that's our main takeaway on the terms of cancellation. And for me personally, it's one of the hardest things to get right in a reactive transactional handling.
Yeah, so probably the takeaway here is if you have to apply things like first and take, do it within the transactional scope, not outside, to prevent all kinds of fancy effects here.
But make sure that none of your users will try to do that from the outside. That's something we discussed in long term internally. As a solution for training material, that we move the take 5 into the transactional work, but then you have to make sure that nobody else can then take 2 from the take 5.
Exactly.
So, and then we would have to apply a solution like what you mentioned yesterday evening, taking the result from the transaction by collecting it into a list on the Flux or on the reactive publisher.
Exactly. So, that being said, we arrived at a good point where it makes sense to make a break. And I would suggest to have a 15-minute break until 14:45. And we will see you back later here. And then progress with R2DBC and Neo4j.
Thank you so far.
Okay, cool. So, let's continue our Reactive Masterclass session. And let's move on with a more technological topic, and this is R2DBC, which stands for Reactive Relational Database Connectivity. Now, why does R2DBC matter at all, or why was it started? See, once we published 2 years ago, or no, it was actually 3 years ago, Spring Framework 5 with a new WebFlux stack, then the only ways how to integrate with persistence and your data were things like with NoSQL databases, with MongoDB, Redis, Cassandra. And it turns out that the majority of our users is past this NoSQL hype, right? We are still seeing folks who are using NoSQL technologies for various kinds of use cases, but really the majority of data is stored in SQL databases. And if you want to access that data from Java itself, then your only option is JDBC. Now, JDBC is a blocking API, and this does not really play well with reactive programming patterns, where all the flows have to be in non-blocking. When we are talking about reactive runtimes, then the number of threads in such a runtime roughly matches your CPU core count, and this is maybe 4, maybe 8 threads. And as soon as you start inducing blocking workloads in such a system, you're basically blocking this limited amount of threads. And what will really quickly happen then is that you lock up your entire system. So using blocking APIs for a quite popular technology, which is SQL databases, isn't going to work in the way we are basically used to it. And this is something that was bothering us for quite a while. And a lot of people were asking us, is there something we can do about? Probably put and offload our work onto schedulers, onto external thread pools, or use some drivers from open source system. So while the answer is yes, you can, it also turns out that this is not the most fun thing to do, because in these kind of arrangements you have to take care of scheduling, queuing work, all yourself before you even come to the point where you can operate on these kind of facilities. When you watch out for vendor-specific solutions like drivers built in the community, then you will see there are a lot of drivers for various databases, mostly the open source ones, but every single driver comes with its own API, and you are not able to leverage the tooling that you already might be familiar with from a Juke or from a Spring Data perspective, right? But you have to use that API directly, and you cannot reuse these kind of tools. And this struck us so much that we had, after a conference, that crazy idea, let's investigate what's possible in that space, whether we can come up with some idea, with some integration that is able to integrate with SQL databases in a vendor-neutral way, using non-blocking technologies. And that's basically how R2DBC was born. Reactive Relational Database Connectivity, which is a specification effort that was built from the ground up with reactive programming models in mind to enable a fully end-to-end reactive and non-blocking integration with SQL databases. To leave JDBC behind, to take the good ideas of JDBC and to improve on areas where JDBC is not as good as it should be. And out of that effort, R2DBC basically popped out. It has two dependencies. So R2DBC itself, in its core, is a specification effort that specifies how an interop SPI should look like. It is not necessarily intended for direct use, similar to JDBC, although there are still people who enjoy working with JDBC directly. But that's a different topic. Now, the specification effort basically says we have two dependencies. Well, we require Java, because it's obviously something that we need to provide for the Java platform itself. And we require Java as of the baseline of version 8 to provide access to all of you who are still working with Java 8 runtimes in production. You can use newer versions if you want to, but we do not want to enforce that. And as you probably might have learned already, the reactive stream specification is one of the foundational parts of reactive programming on the JVM. Prior to Java 9, reactive streams was exclusively available as a third-party dependency from the reactivestreams.org group, and you need to pull that into your code. With Java 9, the reactive stream specification went into the JDK. So we could also have been saying, okay, we want to rely on Java 9 to be fully dependency-free, but this was what really raised the bar of accessibility, and that's why we decided to stick with Java 8 as a baseline. And also given that most implementations of reactive streams are requiring Java 6 or Java 8, it is probably the right thing to do. Now, R2DBC follows a few design principles. And the first and foremost is to embrace the reactive programming nature, to be reactive and non-blocking end-to-end. And this basically means every time we think about a conversation to our database system to initiate some I/O, we return and communicate through publishers at that boundary to prevent blocking at all costs. So this also means, in retrospect, that everything that initiates a conversation with your database will be non-blocking and communicating through a Reactive Streams publisher to you about the success and about initiating even the process. We also embrace the reactive patterns, which is, if you look on reactive code, how it is written, you will fairly often see a very fluent style. You barely keep some variables across a given scope, but rather you pass on with your publishers, with your flat maps, and so on and so forth. And you do not want to retain too much of a state. And this is another thing that went into R2DBC as an idea to make its usage and its consumption as convenient as possible in a reactive programming arrangement. It is more than just a bunch of interfaces. We have a written specification that documents how every component of the R2DBC ecosystem should behave, what you can expect as a consumer of R2DBC, what you can expect if you are a library author that builds on top of R2DBC, similar to what JDBC does, and if you are a provider of a driver for R2DBC, so to say an R2DBC implementation, then the specification will also tell you what you need to provide from an implementation side to comply with the TCK and to be R2DBC compliant. However, R2DBC isn't that typical API like you might know from other efforts that you can fairly easily use within your code, but rather it is shrunken down to SPI, which stands for Service Provider Interface. And R2DBC is primarily meant for driver authors to come up with drivers that implement R2DBC, and for client library authors that want to consume R2DBC in a vendor-neutral way. So you get basically the same level of pluggability that you might be familiar today from JDBC itself. You have JDBC as a standard, and you can interchange drivers below JDBC, and then use any tool of choice on top of JDBC to basically use in your own code. And the same idea is true for R2DBC itself. And in fact, this is one of the key enablers that allows frameworks and libraries to build upon an infrastructure that is reactive and that can integrate with various SQL databases, because now we have founded a common language and a common understanding across all these drivers, instead of us having to rely on very specific driver APIs that aren't interchangeable across tools. Now, the SPI is consists of very few interfaces. And this is by intention. So this is by no means all the classes that exist in R2DBC SPI, but these are the most significant ones that you might work with. There are other things like categorized exception hierarchy and utilities to obtain a connection or a connection factory. But these interfaces are basically the core that represent what an R2DBC driver has to implement. It all starts with a connection factory, which is the entry point to a driver. And a connection factory can give you a connection, and probably you have guessed that already from the name. It can be an entry point to any driver. So any driver has to implement the connection factory, but it can be also an entry point to a connection pool. It can be an entry point to a proxy component that wraps your entire R2DBC arrangement and then gives you insights over latency metrics and these kind of things. So it's very generic what a connection factory can be. The key point there is that it is able to create a connection. And this is actually the second interface in our list here. The connection represents one physical connection to your database, in case that the database is backed by one transport connection. It can also represent a session if you are using a database system which uses a multiplexed TCP connection or other kinds of connection. However, this represents the logical counterpart of what you might already know from JDBC. A connection allows you to begin a transaction, to commit a transaction, to create statements, to create batches, specify transactional attributes. Basically, all these things that are invisible to us if we are using a transaction manager. For us, from a user perspective, the more interesting bit is a statement, which represents basically either an unparameterized or a parameterized statement. So you create a statement by handing in some SQL code into the create statement method on a connection, and you get a statement in return. There is no real differentiation whether a statement is a prepared one, whether it is executed directly, or whether it's backed by cursors. This is all up to the driver. And we think that this is the right thing to do. Well, obviously, otherwise we wouldn't have done it that way. But it's not only this reason, but rather the driver knows best how to execute a particular statement. And this is even true for JDBC. If you take a look today on what you have with a prepared statement, then you see that the prepared statement is basically a facility, a wrapper, to specify parameters to a query. And how the statement is executed on the server side, whether it's prepared or whether you're using some different protocol features from your database server, this doesn't really have a relation to whether it's a prepared statement or a callable statement or just this statement. So therefore, we think it is not important to carry out that fact to the user, whether it's a prepared statement or whatever type of statement. You can execute that statement either by supplying parameters, if you have parameter placeholders, or you can execute it directly right away and then get one-to-many result objects. And each result object represents something like a result set with the possibility that things like stored procedures can supply you with multiple result sets that result from a single stored procedure execution. And the result set can be consumed in two ways. Either it gives you the information how many rows were affected. This is interesting for insert, update, delete. Or you can consume the tabular data in form of rows, and there you can specify either how to get the data by index or by name, and this is your gateway how to retrieve data from a particular result. And then you basically end up with a publisher of the type that you have returned from the row map function, and this is mostly how you would consume it. So really not much that makes up the specification from that SPI surface. There are a couple of drivers available from R2DBC. Some are driven by our own team, and some are driven by the community. So we have drivers that are driven by by ourselves. Is the H2 driver, which is an in-memory database, so you can use that for testing. The Postgres driver is driven by our team, and the SQL Server driver as well. And the community has picked up on various other driver projects, like Google is providing an R2DBC drive for Cloud Spanner. SAP has picked up on the HANA database, providing this driver, and the community has basically picked up with two drivers for MySQL, of which one is a Kotlin driver, and the other one is directly backed by Netty and native reactive infrastructure. So if we take a look on the transaction-specific part of R2DBC, then we will see that the connection interface has three methods which are relevant for us. We have a begin transaction, commit, and rollback transaction. Compare that to JDBC, we have only that set auto commit false mode and no explicit begin. And this is because the JDBC driver figures out itself when it has to issue a begin statement. We found having explicit begin and commit gates is something which makes things more expressive and more usable, and to improve on that area. And as already previously learned, a transaction is still attached to a connection itself. So when you begin a transaction, the transaction will be started for that particular connection. And if you switch to a different one, then you will be ending up in the scope of a different transaction. Since R2DBC is still, and their implementations are still bound to the database protocols, and they are valid for every type of implementation, no matter what your language, programming language is, no matter how you think about imperative versus reactive, so you have still to stick to the database protocol itself. Now, let's take a look on R2DBC code, how this looks like.
Let's see if I still can read SQL queries.
So, let's go into R2DBC, plain R2DBC code directly. So, and we want to reuse the previously known domain with the person table and the person event table. So as a starting point, we again get a connection, and this connection allows us to do certain kind of things, like create statement. And this is really the thing that is important from a user perspective, because that's where we really touch with the SPI. We are specifying our SQL statement here. And as you already see, the number of lines that I need to type is quite significant. So it's a bit more than it was with JDBC. And this is by intent, so. Not to be an unfriendly API, but rather to provide the right abstractions on the right abstraction level. And using R2DBC SPI directly is possible, but it's not the intention to do so. It's rather the intention to leave that SPI to be used by libraries and frameworks. Now, I get a publisher of result out of my statement here, so I need to apply additional wrapping here to make that code usable. And as you might remember, R2DBC depends only on reactive streams, so we have to deal with a publisher type directly. And since this is not fun either in the user space code, we need to use some library to make it more usable. And in this case, we are using Project Reactor, which comes with Monos and Fluxes. I have now the possibility to apply certain functions and operators on my result. So because all this is non-blocking, I need to flat map the result. And the result itself is again returning me a stream of data. So I'm not loading all the data that is available from the query at once into memory, but rather what I'm doing here is I'm consuming the response stream. And this has some significance, because we are not reading all data at once, but rather leaving the data which we do not intend to consume outside of the process, and we consume only the data that we are interested in into the process. So R2DBC also respects back pressure in that sense. The map method allows us to consume tabular data, but since this is an insert, what we probably want to do is consume the number of updated rows. Right, so let's replace this with a method reference, and this is basically how an execution looks like for a simple statement which isn't parameterized. I could decide to parameterize that statement. So instead of having these values directly in here, I could say use parameter placeholders, which look a little bit different than the thing that you might be used from JDBC. And this is because JDBC abstracts also these dialect-specific placeholders away. Right? So every driver needs to inspect and rewrite the SQL statement that you're handing in and replace these question marks with the driver-specific format. And each database has its own version of the parameter placeholders. And this example we are seeing here is now Postgres with $1, $2. So that's the way how they deal with that. I'm able to reference then this placeholder in my bind method and execute it right away. And this is how I would basically use parameter substitution. But yeah, let's go on with that. I also want to insert a person event, and to do so I have a convenience method, so I don't need to type so much of that code. Execute update with a connection, give it some SQL, and then we basically are good to run that method. Now, this was green, and as I told you, never trust a test that basically runs green without telling you what really happened in there. So let's take this query block here, down here, and put it into the auto-commit section to see whether the data has really arrived. And this query block is, again, querying the person and the person event table. Let's run that one more time, and then we will see, yep, we have one row in the person table, one row in the person event table, and if we take that away on the top, then basically our results will be empty. Cool. So this shows that this stuff is actually working, which is good, I guess. Now we can create the same sorts of failures with R2DBC as well, like we had with JDBC, that we basically insert a set of data, and then we insert yet another set of data with auto-commit mode. And they will fail exactly the same way. So this is nice about the consistency, that these things tend to behave in the exact same way. Let's delete the person from the table, add a delete person event with an appropriate statement, which is basically inserts another statement here and another row into person event. Let's run it and see how this goes. It fails. That's expected. Cool. Because what we expected here from the outcome is basically a successful outcome. Let's reformat that so that you can see what's now going to change. And instead of having a try catch in here, I have much more sophisticated utilities to basically say I'm expecting, as a result of my reactive flow, now an error. And this is as good as the try catch with an empty catch, right? And we end up with a similar scenario right now, that we have deleted the row in the person table, and the person event table reflects only a single row. So same behavior, consistent behavior. And if we wrap that into transactions, then we are also good to basically ensure consistency. Yeah, right. So, and to do so, we need to start a transaction. Connection begin. Use the step verifier to synchronize, to issue that activity, and to verify that it was successful. I know it's a wall of code, but it will get better afterwards. We need to begin the first transaction, commit it. Then we will need to begin the second transaction, and basically roll it back. Now we have two blocks. The first one is inserting the person and the person event, which should go successfully. The second one basically is the error case. And what we now expect is that this second transaction is going to be rolled back, and that the person table contains one row, the person event table contains one row. And let's see whether this will basically go. Yeah, I guess that works. Cool. So we have the exact same behavior. The only real thing is how our code looks like and which APIs we use. But the general transactional protocol is still respected. We are beginning a transaction before we are doing work. We are cleaning up after the transaction. So basically the same things like in the imperative flow. Since writing R2DBC code isn't the most fun thing to do directly unless you're a library author, there's a way better way to consume R2DBC. There is this project Spring Data R2DBC that wraps and takes R2DBC itself. It comes as well with an R2DBC transaction manager that brings transactions into your reactive flows, and this is the R2DBC transaction manager. The entire reactive transaction API is is a new thing which was shipped with Spring Framework 5.2, and it supports the @transactional annotation, so you can demarcate your transactional method with @transactional, and alternatively, if you want to have more control, more programmatic control over your transaction, you can use the transactional operator. And this is exactly what we are going to do next. So this is the bare bone R2DBC code. Let's spread a little bit of Spring love in here. Now, to interact with R2DBC via Spring, there is the entry point of a database client. right? So database client. If you are already familiar with WebFlux, you know web client. And web client does for the web what database client does for databases. To use the database client, you have a couple of methods that you can utilize. Right now, we only need the execute method to insert a row and say, okay, we just await completion of that thing that we want, that we planned. So already it is much less code that we need to utilize, and we have much more friendlier methods because in the Spring ecosystem we can be a bit more opinionated about the tooling and the libraries, and we, from a Spring perspective, use Project Reactor to expose our reactive functionality in a way that lets you stay productive even in a reactive space. Let's execute another query to insert the event row. Tell this thing then, and then basically means I do not want to consume any results. I just want to await completion, and this is what monovoid stands for. Let's run this, and yeah, it did something. We do not see anything, so let's add a little bit of assertion in here to see at least on. Oh, here we go. On the console that we have some input there. Oop.
Excuse me.
Yes?
Isn't it actually the situation that when you insert a new column in a table, that often if this has an auto increment, that you expect the ID, that you can use it to update another table. That's like if you have an association between two tables, you insert one, take that ID to fill it in one. So in that case, you would actually expect to block that part. You would like to wait until you get the result and then use that result to update another table.
Okay, so let me rephrase your question. So typically I would expect the database to generate an ID and reuse that ID to run subsequent activities on that. Yes, we can. Let me finish up that demo part, and then I can show you also how to consume the results of an insert statement. Okay. We need to inject that connection in here. So this is, by the way, a great feature of JUnit 5 that you can come up with your own extensions that provide you with some additional functionality. So I have this parameter parameter contributor that manages the R2DBC connection for me, so I can just inject the right thing and the right method. So. We have verified we have one row in the person table, one row in the person event table, so everything is cool. To address your question, how to consume the outcome of such a query. Now, let's assume that this ID here, this one that I'm using statically, would be generated by my database, because that's some auto-incrementing primary key. We can consume that result, and the way how this goes is by either handing in a mapping function, which says, okay, row, let's get from the row, from the tabular data that comes back, the first column. Then I end up with a flux of objects. This is probably not something I want to use, but rather give it a type hint. Say, okay, I want to use it to consume that first entry as a integer. Then I get a flux of integer, right? Then we can take the first entry, because we know we inserted just one thing, and we are basically good to consume that generated ID. And if we wanted to reuse that in a subsequent statement, then the thing what we now do is ID and issue yet another database query that basically takes that. Let's use it here in this place. Spring, by the way, is very keen on keeping your productivity high. So Spring also abstracts away this vendor-specific and dialect-specific notion of parameter placeholders. So you can simply use name parameters like this ID, and I can reuse then this ID parameter to bind my ID, and then do whatever I want to. I do whatever I want to do with this flow. And what now happens is that I'm inserting a row, expecting something to generate the ID, consuming it, assuming that the ID will be in the very first column, and passing on this generated ID to some subsequent statement. And there, by doing so, I'm adding a dependency on the execution, and still my flow is non-blocking, and I'm able to leverage these kind of functionality in here.
I would like to add to that question as well. First of all, I think it's a great question, and it's already a sneak peek into something we have in for special attention, because what we're doing here now is basically one variant of the n+1 query problem at the moment, and our approach would be, regardless whether you would use a graph database like Neo4j or a SQL database, if you can solve your issue you have with one query, with the query language, then that would be probably the better approach in that scenario. Like, for example, in the Neo4j examples we're going to show you, we have the same domain model, and these examples tend to be a bit constructed to show how that transaction handling works. And in a real-world scenario, I would rather use one statement dealing with a node and pipelining it inside the query itself to the next part of the query, and I'm pretty sure that we can come up with a SQL query that does the same for that insertion here as well. So it's always a question whether you want to map and flat map a flux with the next flux inside a transactional block or without a transaction, or maybe try to solve that inside the database. I personally am a big fan of solving it inside the database.
Okay, cool. So let's get on to transactions. So we have seen already a couple of these failing transactions, so this is probably not a thing that we might be so much interested, but probably we want to peek into reactive transaction control. And with reactive transactions, we basically use the similar facilities that we currently have. Previously, we have been in auto-commit mode. So let's insert a person right now. Database client execute the insert, and then do the same for the person event. So what's the then thing? When I execute something in a reactive way, then I always get a handle to the result that I'm getting here. And the result of every execute action is a flux that returns a map from string to object, which is basically a representation of your columns to your values. In that insert case, I'm not interested in the row count or in the actual data that is coming back, and then is a shortcut that allows me to say, okay, do it, and then just come back. So similar to like you would run in JDBC and execute update and ignoring the value that is getting returned. So that is basically then. It preserves the completion, and if you encounter an error, then you can basically get also that error consumed, but it drops the result, if that makes sense.
In that case, it's very important that Mark adds the then, because Mark is using the step verifier. If you look at line 103, we have a step verifier create. Step verifier is a tool to verify the outcome of a flow, and Mark verifies it with verify complete. If the flow would emit items like the map that the database client returns, then the verification would fail because there's no expectation on what is emitted. So if Mark wouldn't drop the items emitted, then the verification would fail. You could verify it by writing down like a ton of expectation on the map, but that doesn't help the code and readability.
Right. So let's go on to the case that should fail. Execute with the delete. Then. And database client execute the insert of the delete event. Then. And now we have chained our execution for the two insert statements together. Let's do the same for this failing part. Without further instrumentation, all this will now result in an error. Exactly, primary key violation exception. If we expect an error, verify error, and let that run, then that was wrong. That was the wrong place to change. Here we go. Verify error. So if we expect that some error should happen, we are still in auto commit mode. Then we see the row in person is deleted. The row in person event is still there. So this is not good. Let's add transactions to that. And adding transactions in a programmatic way is as easy as RxTX transactional, and RxTX is a variable name for the transactional operator, and the transactional operator is the programmatic facility and the counterpart to transaction template that you might be already familiar with from Spring's transaction support, and you can wrap any mono or flux within a transactional operator. And to associate a transaction with your flow, it's as easy as putting as transactional operator transactional into your flow, and everything that happens before this as will participate in that transaction. Everything that will be written afterwards does not participate in the transaction. So the transaction scope is propagated upstream. We have added the transactional scope to the first bit of our work. Let's do the same for the second bit. Reformat it. And by associating this flow with the transactional scope, we will see that a rollback has happened, and we are back to one row in the person table, one row in the event table, and that transaction got basically rolled back. So it's that easy to associate something with a transactional flow.
But we have two separate transactions in that example.
Exactly, yes.
So that's important to notice that the operator does create a new transaction every time it's applied to a flow.
Right. Now, if you don't like programmatic transaction control, let's continue with a transactional service. And as you might be already familiar with transactional from imperative transactions, you can use the exact same transactional annotations on any transactional service with the same implications of visibility and class proxying rules. The only difference really to imperative transactions is the return type, that this insert returns a mono void and this delete returns a mono void. Everything else from the flow and from the idea stays the same. And I'm injecting this, where am I? Here am I. I'm injecting this transactional service here into my method, calling the insert method, using the step verifier to initiate the process and to basically await completion. Let's do the same for delete. We will see a failure because we are in the delete case expecting that it should run successfully. What actually happens is this primary key validation exception. Now let's expect that some error happens. And with this, our test will run green. And we see again a consistent behavior that we have one row in person event. If I remove this add transactional here, probably what will happen is that the person table will be empty. Exactly. And the person event table still has this one record.
So, Mark, I have a question. I've learned in my work with Spring that I could put transactional on a test as well, and I can put transactional on method that return nothing. What does happen in a reactive world with that?
So, In a reactive world, there is no void insert, right? So this is kind of pointless because everything that happens in here would be just discarded. In a reactive world, nothing happens until you subscribe. And if I'm not able to return a publisher from here, then I'm not able to subscribe to anything. So this is something that doesn't work. Also, like you already mentioned, this transactional approach here. See the return type of my method? It is void. So, and how am I supposed to write a test for reactive transactions? Is it something like that? And then return here this guy? No. Well, I could do so, but where's the place for my assertions? I am not able to place any further things in here. So therefore, we decided for a test support to not provide at transactional on test method level, but rather to do the thing that I currently showed you, that you are using either transaction template or a transactional service within your tests. And as time progresses and we learn better how we want to support reactive flows in a unit test scenario, then we will be able to leverage perhaps.
Okay, cool.
So let's continue with our presentation. Right. So a few specifics about transactional. So the transactional annotation usually takes a transaction manager as an optional argument in the attributes. And to distinguish whether a transaction is a reactive transaction or an imperative transaction, the actual called method signature helps us. If the method returns a known reactive type, this can be a publisher, mono, flux, RxJava single, observable, flowable. This can be any Kotlin suspended type, so a suspendable method. This can be a Kotlin flow. This can be even a completable future. In all these cases, we initiate a reactive transaction, and we expect that the context ships with at least one reactive transaction manager bean. Otherwise, we fall back to imperative transaction management and reusing the platform transaction manager. So really, reactive transactions are an individual separate code path which is activated if you have the right dependencies shipped on your class path and if we encounter any reactive method.
Are they mutually exclusive in a given context?
Yes. So this is a good question. So let's basically draw that in code. And say, hey, we have this nice transactional service. And at some point, I decide to inject also JDBC template. JDBC template? JDBC template? No JDBC template for me. Probably I didn't have that appropriate dependencies in my class path. But still, JDBC. Let's assume it would be there. And add an appropriate constructor, so we have less red code. Now, see, I could have something like delete in JDBC, right? So and do crazy things with my JDBC template right now. Methods would be probably the same name without then or beloved then. And this would be look how I would go about an imperative transaction, right?
Yeah.
So there's probably nothing wrong with that. So your question probably was like, what happens in this case?
Yeah,
right?
Of course.
And you probably remember this transaction binding to a connection.
Yeah.
Now, although we might point to the exact same database from JDBC and R2DBC, each of these technologies maintains their own transport connection. So JDBC has a connection channel to the database, and your R2DBC driver might have one. And you know, the transactional state is bound to that connection, and we would deal with two connections and two transactional states in here. So there is no way how to propagate an R2DBC transaction to a JDBC connection and vice versa, because these are entirely independent technologies in here. And even besides the fact that you should not block in your reactive code, and every time you block a thread in a reactive code, a kitten dies, and we do not want a kitten to die. Right? Cool. What else? Well, we have seen a transaction, we have seen a transactional operator, and now let's discuss this concept of escaping data from a transaction. Now, due to the push nature of streams, and even to the streaming nature of the utilities that we are dealing with in a reactive programming environment, it is possible that our mono or flux already emit data to somebody else, although the transaction is still in progress. And this is actually a desired state, but we need to be aware of that. Now, how does this look like, data escaping? So we have these transactional tests that do a load of stuff, actually. And what happens here is that we are loading data from a CSV file into our database, which is coordinates of Starbucks. And we are loading 1,000 records in here. So this means this transactional thing here loads all the 1,000 records. Afterwards, we are executing a select to return all the rows that we have stored in our database. And we are verifying that these should be the number of 1,000. And to make things sure that they are still there, even outside of the transactional scope, we have this select count everything from Starbucks to have 2 verifications. Now let's run this and see how this goes. Okay, cool. We have 1,000 rows. Now, to illustrate a little bit what data escaping really means is that we need some way to visualize that we got hold of the data. And what's better than a system out? So system out for the win. And let's run this. But before we run it, make it beautiful, because we care about our code. And we will see a lot of output and a lot of noise on our console, right? So although we are within the process of our transaction, we are still getting the data outside of the transaction. Now, what could happen, probably, is that something evil happens then suddenly in our flow, right? So let's assume that that we have something that fails at some point in the processing, because Reactive is all about stream processing when it comes to the way how we think about that, and assume that we have some processing error on one of these records, and to simulate that, we are catching a particular store number. And if this equals to some arbitrary number, what we do is we simulate that some error happened. And for every other store, we just propagate that data as it would be just sent. Cool. So when we encounter this particular number, we will complete that processing with an arrow, which will happen, which will trigger a rollback. Now, I know, because I did this demo already earlier, that this is after record 149. So let's run this. No, it's probably not record 149, but still, well, it was record 149, but what I didn't catch was this runtime exception. But still, it already visualizes us that we have seen all these records, all these rows that are emitted to system out because they come out of the transactional stream, and suddenly some error happens. Now let's make this test green again. And basically come to the point that we have seen 149 records, all these. And afterwards, when this processing is finished, and we run our select count query on the exact same data set, we see, well, there is no data in there. So this is something that you should be aware of these behavioral changes, that you might see data coming already to your process instead of being atomically processed before it finishes the processing. There is a thing we can do about that. So instead of reading the stream here, we can basically collect all the data. Let's go for collect list. This will require us to use a mono, because now we expect one row or one item. Now I screwed up something, probably. Oh boy. No, it's still not going to work that way. Flux list map. Okay, yeah. The reason for that is because the execute method always returns flux. Yeah, so forgot about that. Yeah. What am I doing? I'm fixing it. Okay, cool. Now, the thing to recover from that scenario and prevent that data is leaking out to some process before you have seen it is basically to collect it into a list. So basically drain all the data from the buffer and from the wire, buffer it into a collection, and then emit that collection only when this processing was successful. This kind of works, but you then lose this streaming notion of reactive programming, and you have to have sufficient data and sufficient memory in your system available, because you need to collect all the data up front. You cannot just collect it and get rid of it like you would in a stream, but rather you have to buffer it in some way. Now, what we see is no data leaking, so there's nothing. And somewhere we have well, because this is terminating directly with an error without emitting data, we have seen this assertion error basically, which where I falsely assumed, okay, I expect one row and then I expect an error, but what really happens is that no data is emitted at all. It's all being collected and aggregated, and my setup now finishes without leaking the data to any consumer. And whether you choose this way or the other pretty much depends on your setup, but you should be at least aware of these changes in behavior. There are a lot of other fun things that you could encounter with reactive programming and R2DBC, and where you really feel the nature of this stream-based processing. See, R2DBC really translates all the incoming frames from the transport stream directly into your application. And if you run into scenarios like with N+1, where you run a query, during the query while the query is active, you issue sub-queries, then this can cause a bit of congestion. And you can easily end up with scenarios where you basically congest the entire stream. So as Michael already said, if your database provides you with things like joins or graphs as a way of returning it, use these kind of things instead of running a query, and while we get data, run a sub-query, because this automatically is able to lock up your entire application. And this is due to correlations with back pressure, prefetching, and how many data is still on the stream. Because while we are consuming the response stream of the first query, we are issuing sub-queries, and the responses get appended to that response stream. And once we reach a certain threshold, we are no longer able to progress with our application, and this will ultimately cause lookups. And let me show how quickly this really goes with this lookup. Now, we have again our Starbucks example here, where we are selecting the data, creating a subselect. Everything is cool. We add reactive transactions to that. So associate a transaction with our upstream publisher as transactional. In this case, still everything is okay because our implementation of R2DBC is the H2 in-memory database, right? So let me switch quickly to Postgres. I have a different extension here for Postgres. And now we're using the Postgres database. And suddenly, basically, what happens is that I run into an exception. And this is some sort of I/O exception. Now, why is this? The reason for that is because our query arrangement uses flatmap. And this basically means start a lot of sub-processes to issue a number of additional queries. And since we are using R2DBC without any connection pool, we are basically unbounded in the number of connections that we are opening. Now, to fix that, let's use that connection pool in here. And the connection pool will guarantee us that we have an upper bound. So the Postgres database is no longer it is no longer rejecting our attempts to connect to basically to the database. Now we are green again. This is cool. So we are running now with a connection pool. Let's add transactions into that. And as you might already know, transactions will cause that we will bind a connection to the transactional flow itself. And even if we would wait perhaps for a couple more hours, nothing really happens, because while we are reading the stream, we are appending responses to the input to the stream we are reading, because we are issuing queries. The database is responding, but the responses are queued behind the current response. And we do not really get to that point until we either stop doing these stupid n+1 things, or we add a crazy amount of prefetch to here. But in any case, these aren't arrangements that you want to encounter during your production setup, but rather you should think about these things up front and ideally preventing these.
So we have to say that those issues are not tied only to the R2DBC implementation specification. Our driver exhibits the same behavior, even though internally do connection pooling. But if you try a bit, then you can find yourself in the same edge corner of the room, I'd say, and nothing you want to do in production. Right?
Perfectly. Cool. And this brings us
to Neo4j. So I have to get up a bit. Neo4j, anyone in the room worked with Neo4j already? Oh, that's great to see. Nice. Neo4j is a database. It's a graph database, and it is a so-called property graph database. Don't worry, I'm not going to bore you too long with the details. Neo4j is also an ecosystem. I personally work on the Spring Data team at Neo4j. I see Mark as friend as colleague, but he works at Pirte, the Spring Data team. But we happen to work a lot together on that stuff, and I can tell the story from a vendor side implementing on reactive streams and on reactive Spring Data Neo4j, and I find that story quite interesting. Some of the stupid question I just asked regarding the transactional on tests that actually bit me into while I was writing tests for our reactive transaction manager. I have written down a test for it like I would do with a standard transactional test and put a transactional on the test and nothing happens. And I also had one service for a test case where I put the transactional on a void method, and had another method returning a mono or flocks or whatever. It doesn't matter, it returned a reactive type, and suddenly Spring Context was yelling at me that I was missing a platform transaction manager. Right, great, thank you. So there are two different paths that can be taken, but they are decided on the return type, and they are not that mutually exclusive. So they can happen to be in the same service, but that's of course nothing that is recommended. So I work at Neo4j as part of Spring Data and also of the drivers team that gives me a lot of insight what my colleagues at Neo4j are doing for the drivers, and so I can tell the story from that side as well. So back to the property graph. A property graph consists of nodes or vertices. We call them nodes in Neo4j. And you spot them by looking for nouns. They represent usually objects. Picking up the theme that Mark already did with Breaking Bad fits nicely into our demo. We usually deal with a movie graph. So the nodes can be person who acted in a movie or directed a movie. So that's the second thing of the property graph, which are relationships spotted by verbs. Most of the time they represent some kind of actions. Both of them, nodes and relationships, can spot properties, hence property graph. In this case, nodes having names, and on the relationship we store the role. We said Neo4j that this whiteboard model easily fits the physical model, so there's no big need for remodeling stuff. And that is a screenshot from the Neo4j browser interface exhibiting our standard movie graph. And that's something I'm going to show you just a little bit. Be aware that is not my machine. My demos are going to be a lot less smooth than Mark's. Expect some hiccups there. So already happens. The mousepad is different setup than mine. That is the browser interface of Neo4j. And if you want to learn that stuff, we have some useful, I cannot even do that. We have some useful guides built into the database. The movie graph, for example, you can just click your way through it. At least one can try. And you can create your first graph database set like this. We also have a tabular result. And what I'm going to use in my reactive demos is something that we call Cypher. That is a declarative query language for our graph. Cypher influences the GQL standard specification a lot. That is a new ISO specification coming up in the next years. Maybe you will see a lot more of this kind of queries in the future. I can match a node of type movie. The movie is the label of the node, having a title like the metrics, and I can return all persons, all people related to that node, and that's the same we had on the slide beforehand. So to keep consistent with the topic of Breaking Bad, something I would use in my demo would be a person named Aaron Paul. Aaron Paul is the person who played Jesse Pinkman, and we can model that as well by matching that person again by its name, Aaron Paul. And with that person, we can create a relationship from that person. Relationship having a type, acted in, and the role has been Jesse Pinkman, I guess. And the movie was I'm slowly getting there. Breaking bad. And return all the things. Right? That's what mousepad is killing me. That's just going to be fun today. That's what I mentioned beforehand. If you have a query language or whatever to do steps inside the database, just do that. It helps a lot to make stuff a bit more understandable. So that's the advertisement part on Neo4j, the database itself. I was running the examples on the current production release, Neo4j 3.5. Upcoming in the early next year, I think, will be Neo4j 4.0. 4.0 is a big effort, a whole company effort, I'd say, across several teams. Mark mentioned that Reactive implementations have been first and foremost started with other NoSQL databases. Neo4j didn't have one. We wanted to get this right. We do this up to the database, up to the Cypher execution engine. The Cypher execution engine and the server knows how to deal with back pressure. It knows how to answer a request for a given number of nodes or records. And also part of that are drivers that work with back pressure as you expected. I don't know if he already said that this reactive programming is not about only making things faster or more performant. It's about making things more resource efficient, and back pressure is a big deal about making things more resource efficient, and we want to get this right. And the big part where my team and I is working on is Spring Data Neo4j RX. This is a public preview of a Spring Data module that eventually will replace Spring Data Neo4j as it is now. Spring Data Neo4j RX supports both imperative and reactive transaction managers. So we've seen a lot about how JDBC works, how to deal with raw JDBC connections. Now you have to endure this with the Neo4j Java driver. All the drivers we offer for several languages have the same building blocks. The building blocks we have here in blue on the left is the driver itself. The driver does connection pooling internally for you. We have the session, and with the session as a one-to-one relationship, the transaction. Transactions are bound, or session is bound to a transaction. And we have the statement result, either producing records containing nodes and relationships, or something like we call statement summaries and result counters. So we can also get nodes created or modified, relationships created and modified. The life cycle of this is that the driver owns owns a connection pool, and the connection pool contains several connections to possibly different servers. So what the driver in our case needs to do or should do is to be able to do routing. If you set up a Neo4j cluster with leaders and followers, then the driver is responsible for looking up a routing table to everything it can read from and write to. When asked for a session, the driver spawns a new one, and the session then borrows a connection from the pool when you ask it to open up a transaction or just run a query. So the session is our logical concept over a connection. And I would say the bold driver, or the drivers overall, have learned a bit about from JDBC. We make a much more explicit differentiation between auto-commit mode and what we call implicit mode and explicit transaction handling. So everything we run on a session itself runs in auto-commit mode. There is no way to say this thing does not run in auto-commit mode. You can handle a session as a resource in a try with resources block, and everything in that block will auto-commit. If you want to do explicitly, you have to tell the thing to do it explicitly. Yeah, I already said that. The the connection will be eventually bound to a transaction. So challenges we had there is that we want to support as a vendor several ecosystems. So there is not only Spring, there's even not only Java. There's Java, JavaScript, .NET, Python, Go, and it's the I missed the Python driver here. Java, JavaScript, Python, .NET are the main languages we support directly. There are some community drivers for other languages as well. And we want to keep the surface, what the drivers expose, very similar across languages. So in case someone switches from being a Java developer in the Spring world to data scientist and running Jupyter notebooks on Neo4j, he should have a similar experience with the driver. So it's not enough challenges. We already have 2 APIs on each of those drivers. One is the standard imperative blocking API, friendly, everybody knows how to deal with blocking, you just write it down and you're happy. But then we have also an asynchronous API. In .NET, it's pretty much everything asynchronous. And I just recently learned while learning about our .NET driver that stuff in .NET looks very similar, like coroutines in Kotlin and lightweight threads in Project Loom in some future Java version. I like that approach a lot. It's easy and understandable, and it's much less code than dealing with Reactive Streams API. And we want to support that in all languages. So the matrix of things you want to implement is growing increasingly if you want to have that experience, not only in Spring World. So as a first step with Neo4j 4.0, we have reactive support coming up in Java and JavaScript and .NET. The Java driver has already been released in several beta versions. You can try this out, and it's already in the resources we presented. So how does that look like? I try to split this in 2 parts. I have slides for every demo. I'm going to try to give the reactive demo on Mark's laptop. I'm not going to promise they work flawlessly. So let's first have a look at the imperative version only on the slides. So that is our auto commit mode. We start using the session as a resource, and we do something with it. I create a person here. Our approach to named parameters is the $sign. When such decisions are made, you never can predict the future. In Kotlin, you have strings that are interpolated. So, and the $ in Kotlin is not useful if you have multi-line strings in Kotlin. So I try to write down Kotlin code that way. But that's just the way it is, right? You made a decision about an API and about placeholders, and in the future then there comes something different along. Anyway, that is nice and easy. There's an implicit transaction. It's committed after the resource close. It's done. Easy to understand. The next one is what we have, or what we call is transactional functions. That thing is quite useful if you want to deal with various low-level functionality. At first look, it looks similar to the previous slide. Session is a resource, but here I pass in a lambda, can be a function reference as well, to a method called writeTransaction, and that lambda gets a transaction handler, and on that transaction I can run stuff. The advantage over that approach is not that I now deal on the transaction. I could also do an explicit rollback on it, but I can take that unit of work and give it to the driver and let the driver handle all the things. That helps the driver to help you when there are some transient client exceptions that can happen. In a cluster setup of Neo4j, there can be scenarios when there is a leader re-election, and that's something that our driver can handle. And if we pass in a transactional unit of work as a whole to the driver, then the driver can do a retry for you. the driver cannot do a retry if you use implicit transaction, and he also cannot do a retry if you use explicit transaction, because how is the driver supposed to know when the unit of work is over? So, or what belongs to a unit of work? But there is a way to deal with explicit transactions. I can ask the session to begin a transaction and run several things on that transaction. It's always the same example, creating a person, and then commit it eventually or roll back. Having such a thing like explicit transaction, I think it's necessary for higher value libraries like Spring Data Neo4j to implement transaction management. Otherwise, I would not be able to, I think, deal with mapping those kind of sessions and transaction to a resource in the transaction manager. So, trying to have a look at reactive transaction. Now the fun starts. So the project we shared contains several implementations for several databases, and what we have is no. How can I make this bigger? Okay, we always have transaction tests and transaction exercises. So the tests are fully containing the whole example, and the exercises are basically empty. And as Mark said several times, the tests in those are red by default, and the exercise is to make them green. And and I'm going to try to make the Neo4j tests green. So in the test I use the same JUnit 5 mechanism to write my own extension. That extension brings up an embedded Neo4j instance. That is possible. Neo4j is written in Java. You can use the embedded version for tests, but that's as far as I personally would go with an embedded database. So if I run that autocommit test now, then I have Java 11 warnings and an expectation that fails. I expect that at least one node is created and one relationship is created. I have the same approach like Mark did. With two fluxes, and I'm now asking the driver. I skipped a slide, but it's fine. The driver offers a very similar API to R2DBC. On the top level we have an Rx session, that's our marker for reactive sessions, and on that we have methods exposing publishers, like a publisher of Rx transactions, or run that executes stuff, exposing publishers of records, that's the actual result. We can expose the summary as a publisher and the keys. So our driver is similar in that aspect to R2DBC, like it does not pinpoint you to one specific reactive library like Project Reactor or RxJava, but exposes the vendor neutral reactive streams types. So, and I'm using the reactive session of the driver again as resource, passed to a flux, and on that session I'm now building the complete flow like this. return. And eventually I have to close that session as well. I think I'm missing something again.
Come on.
Where? Ah, yeah, at the top. That is very funny how different a keyboard layout can feel. So the test will still be red, of course, because I'm unsure which keyboard shortcut does reformat my code to be nicer. So the test is still red, of course, because the flows are empty. So I now can create a person very similar to what we did beforehand. We also have on the same level like R2DBC that I need to write some boilerplate code to actually create a flux from it and have some convenience method to extract the summary counters. Result. So first of all, I actually have to execute that by either asking for records or the summary, and then I get the counters and can delete them afterwards. And I can do the same for the movie. The query is a bit longer. So in a real world scenario, again, I would run this as one query, but we try to model the examples all in the same way that you can find yourself around.
But you know, Michael, you're out of the future. This is El Camino. This is not Breaking Bad. Hopefully, you're not going to spoil anything.
I won't spoil it, but I haven't seen it yet as well. But I wanted to be consistent because Breaking Bad is a TV show and not a movie, so just to be super consistent here, right? Yeah. After that, the test should be green. Did I actually hit this? No, I didn't. So while we wait for that to turn green, question could be arise why I expect only one node created and one relationship where I actually did create two nodes, like the person Aaron Paul and the movie. That is because the then many does not concatenate the streams I have. If it would concatenate the streams, then the result would be different. Then the result would be not number of nodes created equals 2 and relationships created equals 1, but it would be 2 summary counters, so the expectation would be different. Expect next matches something like the first one should be having only one node created and the next one something like that. So that while this is not very transactional specific, it's specific to programming in the reactive style. There are some details you might oversee when reading through the API of any of those reactive frameworks. The operators and methods may look similar, but do quite a different thing. And I really like the question about the then in the code. That's something I often stumble upon while working with it. I ask you several times about why does that stuff not work, right? So next thing I want to show is we can also deal with a rollback. I'm going to skip the auto commit with error because we are only 20 minutes left. Rollback in a transactional, in a reactive way is, I think, something you can get very, very wrong. I want to do in that thing here. Also, I want to create one person, the same model, and roll it back for whatever reason. The first naive approach would be, so here I'm working with the session as resource. I cannot do this when I want to do explicit transaction. So I just copy that out over here, and then I build my flux using the sessions begin transaction. Nope. I didn't want to do that. I want to build it directly, and then flat map it and do something on the transaction. So that will be closed afterwards. And this is of course wrong because it's not a supplier. Begin transaction. So that test will not roll back. I have a verification in place that checks if the person has been created, and that verification expects nothing. So test is red because I haven't rolled back anything. So in a very, very naive approach, and I'm just gonna kill a kitten right now, you could do something like that. Introduce the step verifier and wait for the thing to complete. So that sorry, but I wanted to make sure that this flow created here interacts with the database. Otherwise it wouldn't be meaningless, I'd say, to do a rollback. But it would be something I would maybe expect in some issues, right? So if you do an explicit rollback, nothing works. Okay. Demo gods don't want me to kill kittens. That's great.
And they know what they do.
They know what they do. So this is green, but it is also bad. My preferred approach to that would actually deal with business errors. Okay, so I just copy that flow code. So no, I don't copy the bad stuff, only the good one, and replace that here. That's the next test. So, and here I'm using the transaction as a resource, which is nicer on its own. And I use the using when overload of the flux that allows me to specify what should happen on success in line 104. On success there should be a commit. On line 105, that's the handler for the error case. Then the rollback should happen. And in line 106, that's the handler for the cancel case. And for consistency of the demo, I just agreed that the cancel case will be also a commit. Sorry. And to introduce an error, we can just emit a mono containing an error, throwing a business error like that. And we should probably remove that return and something like that. Test is green now, and what it gives us is a scenario where the error handling is outside of the transactional work, explicitly acting or reacting on the error happening. Maybe it would also could be a business error that actually can be committed, whatever you want. Okay? So that is our take on the reactive surface of our driver. So that was the slide I mentioned. I did skip a bit. We have seen implicit transaction. I can directly work on the session and pass it to whatever library I prefer to not have to deal with raw publishers. We haven't seen that. The transactional functions are still there. I can pass it on to a reactive overload for the write transaction or read transaction method on the reactive session, and then work on that. Here the same thing applies, that the Neo4j driver is able to react on certain transient error cases. That is important to know if you maybe have a setup of your database that need this. We have seen the explicit handling of transaction. To be honest, especially in the reactive world, the explicit transaction handling of our driver looks very similar to the transactional functions. I can refactor that code to extract the method I want to execute, but that explicit version here does not deal in the unit of work like we've seen before. So for the last couple of minutes, Spring Data Neo4j RX, or SDN RX for short, that is something that is in a public preview right now. That Spring Data module has been written from scratch, and it does differ a bit from the current Spring Data module for Neo4j. So the current Spring Data module for Neo4j tries to cater for a lot of use cases, and it does that by being split into two parts, like Spring Data JPA and Hibernate or Eclipse Link behaves to each other. In SDN, current version, we have Spring Data and Neo4j OGM, where OGM stands for Object Graph Mapping. And it caters for embedded scenarios, it caters for HTTP scenarios, and so the database can be accessed via an HTTP endport as well. And it caters for accessing it via the Java driver. So that would add complexity for dealing with reactive stuff, which does not work very nicely in our setup. And OGM has something very, very special. It tries to rebuild the graph which is inside the graph database as one-to-one in the object space. That is nice if you need that, but is very difficult from an object mapping perspective, because it needs to read the whole result set to recreate relationships of certain types. So that doesn't work very nicely with dealing with back pressure, because how can you not consume results if you need them to rebuild the object graph? So we try to be a bit more modular in the design of the thing, especially for dealing with reactive, but also with other ecosystems like Kotlin, where immutability is a big thing. We want to have the domain being able to be immutable. We cannot do this currently with OGM. We only want to have one layer of stuff. So working with Spring Data itself has been tremendous pleasure, because it has a mapping context that gives you as a library developer tons of information about what a user is doing in their classes, how one expects relationships or something to be mapped. Currently we do this on our own in the OGM implementation, so that's the duplicate work for basically nothing. And we rely 100% on using a driver and don't do embedded at the moment. It has some new features. I think it's one of the only stores at the moment supporting all the find by methods you have in your documentations, and I really like that. of course, we integrate with Spring 5.2 Reactive Transaction Manager. Yeah, and that's the way on how we integrate with it. We have on the lowest level the Neo4j database and the driver, which we've seen. Basically behaves a lot like the R2DBC SPI. We have a Spring Boot starter for that nowadays. So if people don't like object mapping at all, but likes the automatically configured driver, they don't have to pull in OGM anymore or a project they don't actually use. So you can pull in Spring Boot starter for that. And starting in the box, we integrate with Spring Transactions. And we thought that it would be a good idea to do that in 3 steps or 3 escalations. We have a Neo4j client, pretty much like the database client or the web client, with a fluent API to execute queries, bind parameters, execute them. On top of that, we have a Neo4j template that knows about your domain mapping. And yeah, on top of that, we build Spring Data repositories. And all of them integrate with everything Mark said, with a transactional programming model and with the active transaction operator added to it. So I'm running out of time. I'm going to skip those demos for good. It looks like you said, you've seen with the R2DBC client, we can execute queries. The mapping is up to you or up to the users. I think that's a pattern we see in several places at the moment. There's this Spring Data JDBC initiative. People are finding that query languages are actually a good thing to have, and that our frameworks should not make it hard to use query languages. We follow the same approach here. The query language not being SQL but Cypher, but doesn't matter. The principle is the same. I don't want to hide something powerful from my users to use it. So that's the Reactive client. The Reactive template would look like this. Basically, very similar to what people are used in Spring Data, MongoTemp. I think the Mongo template works the same way. And yeah, the repositories, it's just plain Spring Data repositories. Like people either love or hate them. I love them actually. Yeah, transactions. I cannot add much to it. That's the same like you can copy Mark's code from the R2DBC demo, replace the domain a bit so that it fits into the movie graph or whatever graph you have, and then you can use a transactional with the repository service, or you can inject the transactional operator into a flow and you're done. Yeah, and I have to say that I really like that joint effort across several companies actually to implement that, and it was really helpful all across the board for everyone. So what we needed to do to implement it, use explicit transactions. Inside our implementation, we use one driver instance as lookup for the transactional resources. We bind the session and the transaction, which is already a pair that belongs together, into the transactional resource. And formulating that in a Spring way is the code we've seen before. We need a session that is done by Flux using with the session as a resource provider, then the actual work. In the actual work, we need to start the transaction. Then your stuff happens. And then, depending on cancellation, commit, or an error, we need to handle that. And afterwards, stuff gets closed. In reality, it's a ton of code, but it wasn't that hard to implement. Having said that, I would not recommend doing it on your own. So, it's nothing. But we see that sometimes that people run their own transaction manager. And as we seen in the first couple of slides, there's always some or more edge cases you may not have thought of, and maybe we haven't thought of as well. Can happen. But if we solved it in one central area, then I think it's better for everyone. And yeah. So if you want to have a look at Neo4j, we have some resources. We have a download for it, several instances. I just leave you with, I think, those URLs. There's like 4 minutes left for questions.
Yeah, I think so. So I think we can still take 1 or 2 questions if you have any. Yes, question.
On the data escaping part, what's the main thing that I should look out for when I start coding transactions?
Okay, so the question was from a data escaping perspective, what should you look for when you start out with working with transactions? So it pretty much depends what your use case is, and although this is a very generic question, it boils down basically to 2 decisions. If you are processing data in a transactional way and you want to reuse it outside, it basically depends on whether this outside can deal with replays, with rollbacks. So if you want to put it into a log, then probably you're fine. But if you are processing data in a transactional way that cannot deal with rollbacks, say you're putting it into some event store that takes your output and then puts it into some other place that relies on that this transaction has happened, then you need to collect the data upfront, like we showed with buffer and collect list, and only start with the subsequent processing when you have that guarantee that the transaction was successful, if that makes sense. Any other questions? Yes?
Not super related to the session, but Josh mentioned this morning about tailable. Does the driver support that?
Okay, so the question was, what about tailable? This tailable cursors pretty much boils down to the data store that you're using, and Josh was using earlier this morning MongoDB, and tailable cursors is a feature specifically of MongoDB. It has no real touching points to transactions, but rather what MongoDB is doing there is they are streaming the transactional log, so change data capture, which usually happens when things get committed.
So if you want to get real hacky, you could write a Neo4j server extension plugging into the transaction events and do something like that. But as Mark said, it is not something that would work nicely with transaction, I guess.
Right. Okay, there was a follow-up, and what about Postgres? Well, good thing is Postgres has this feature called logical decode, and you can consume this write-ahead log that is Postgres giving you as a replication stream, currently via the PGJDBC driver and through the R2DBC Postgres driver, and really consuming that write-ahead log, this replication stream. Well, it is already a stream, so it makes a lot of sense to consume it also in a streaming way than reserving just some silly thread that pulls on the connection. So yeah, it is possible. That being said, I hope this presentation was useful to you. Enjoy Devoxx. Thanks for attending.
Thank you.